A distributed system, also known as decentralized system, typically communicates by different processes, right? Now, in this particular lesson, you're going to learn how communication happens within a particular distributed system. So, as you can see from the diagram, a given process A communicates with another process. Now, this kind of communication is what we refer to as interprocess communication. So we're going to understand the two categories of communication, which happens both or either asynchronously or synchronously. So to learn more about this kind of process communication, kindly stay tuned until the end of this particular video. All right, thanks and happy learning.
Hi, hello Lana, welcome to Lana's Coach. Now we are going to look at the interprocess communication, and this is actually a way of how two different or more than two processes communicate within distributed systems, right? So the concept of inter-process, that means we must have more than two processes communicating, right? So we're going to look at different things regarding to how maybe the client server communicates, how the external data is represented, and of course understanding the various protocols that guide or aid this kind of communication. Again, you're going to look at how different forms of communication happens in a group form, talking about multicast kind of communication, right? So what is interprocess communication, right? So these are mechanisms that allows processes to communicate and to synchronize the actions without sharing the same address space. This brings in the concept of transparency. Yeah. So if we can be able to establish a communication within a distributed system, then this particular kind of communication should ensure that there's kind of some form of what transparency, right? So we're going to look at different jargons and maybe what happens when two processes communicates. Yeah. So basically, the exchange of data between two or more separate or independent processes or threads. Yeah. We can look at it from the angle of how operating systems establish this kind of communication. We can better still look at communication that happens within the network. Yeah. Now, what you need to understand is that inter-process communication happens in different ways or in different environments. Yeah. But we're going to look at not only within the operating system environment, but also maybe how communication happens within a client server environment, right? So this particular communication can be guided or represented with other third party uh, kind of applications, yeah, like we have the APIs, yeah, that can always ensure that this communication between the various processes is well established and executed, right? So distributed computing requires information to be exchanged among independent processes. Now, we looked at in our previous video the various characteristics of distributed systems, and we realize that one of the characteristics is transparency and also reliability and so on. Yeah, so we need to ensure that the communication that happens between the various processes and improves these characteristics like transparency, reliability, and so on. So should we have problems between inter-process communication, then we will have problems when maybe realizing how distributed systems are implemented. So we have the different aspect of how processes execute their communication. The first approach is where two processes communicate between themselves, right? And the other scenario, we have a particular process communicating with different processes in what we refer to as multicast. Yeah. So you can always be confronted, or processes can always use these two scenarios to communicate, irrespective of which approach that the process used to communicate. We need to understand what happens. How does the sending process execute the communication to the receiving processes? So we're going to look at the operations that are required to be fulfilled in order for communication to be to happen, right? So like we are going to look at the receive concept. Yeah. Within the receive concept, the sender must always be sending a particular some kind of message, right? We also need to see how the connection happens. How do we ensure that the sender and the receiving process can establish the communication? Yeah. So we looked at maybe the transport layer. We looked at the two common protocols. That is the TCP that offers the connection-oriented communication, and the UDP that offers connection-oriented communication. Yeah. So as the various processes establish the communication, we also need to identify, are they using the UDP option or they're using the TCP option to send message, right? So on the other end, the operation send and receive. Yeah. Also we have the disconnect. Once the connection has been established, the data has been transmitted, then the two processes must also ensure that they can be able to do it, to disconnect their communication, and that only if it is connection oriented. Yeah. Connectionless, you can't really have some kind of disconnection anyway, right? So within the distributed inter-process communication, we need to understand or answer these vital questions. So how do we support communication over a network? Do we have the right infrastructure? Yeah. Do you have the protocols and so on? How do we hide this distinction between local and remote communication? We're going to look at maybe how the remote procedural call, yeah, or using the stub way of maybe having some kind of abstraction layer, so that we present some, we eliminate some technicalities when two processes communicate remotely. How do we then deliver information with minimum latency, minimum disruption, ensuring maximum throughput and minimum jitter? Yeah. For two distributed components to be able to communicate, we also must ensure that there is minimum latency. Yeah. As we say, that latency is that period of time that maybe a particular process releases a particular message and the time the receiving process receives that particular message. So if it happened fast, then you can say there's some kind of minimum jitter. So how do we ensure security during the inter-process communication? Yeah, and also how do we shield one process from other process failures? Yeah, do we have the transparency, enough transparency levels? Yeah? So all communication in distributed system is based on low-level message passing. Yeah, we need to have some kind of form of message passing for us to ensure that there's some kind of communication. Yeah. So we're going to look at a scenario whereby, or the unicast option, where a particular process communicates with another process. So we can assume that process A builds a message in its own address space and executes that and sends that particular message over the network to the other receiving process. Yeah. So again, I'll make it clear that we have different environments that communication can happen. Yeah. This inter-process communication can happen when you look at the various operating system. We looked at also the middleware, some form of applications, right? And better still, you are going to look at this form of communication or inter-process communication within a network. So what do we need? We need a good network infrastructure. We need to understand that we have the various efficient protocol. Yeah. Also, we need to understand the transport protocol. Yeah, and the communication models that we're going to look at, client server, right, and so on. And of course, we need to ensure that there's some kind of security when these particular processes communicate within the network. So as I'd mentioned, we have other additional applications that will support this kind of processes. So we need to understand the various concepts when it comes to two processes communicating. Yeah, like how does the server client server communicate? Yeah, we are going to look at the remote method invocation, and I mentioned also the remote procedure call, right? Also, how do the various processes communicate when you have two or more processes? That's what we refer to as what? Group communication. Now, when we talk about RMI, or remote method invocation, it allows an object, yeah, to invoke a method in a particular object. Yeah? So we're going to look at maybe the examples of Java and so on. We also have the remote procedure call. Yeah? This allows a client to call a procedure in a remote server. We are going to see how the stub is implemented, so that we have a kind of a replica mechanism whereby instead of a server actually remotely communicating with or directly communicating with a client, we can have some stubs that can have some kind of procedural call just to create some kind of what? Transparency. Also, we need to understand the request reply protocols. This is how the various client and servers are going to communicate, either in form of RMI or RPC, and of course how group multicast protocols are designed to support this form of what? Communication, right? So just know that a group multicast is a form of inter-process communication in which one process is a group in a group of processes transmits the same message to all members of the group, right? So to understand this further, let's look at the various characteristics of the inter-process communication. Yeah. So what are those, or what are the characteristics that a particular inter-process communication must have? Now, the common one is the synchronous and asynchronous communication. Now, when you understand these two terminologies, then I think you are ahead to understand how the inter-process communicate. Now, two ways, or two major ways that various processes communicate is either synchronously or asynchronously. Yeah. So in the synchronous form, both send and receive are blocking or apply the blocking technique. We are going to see that, right? On the other hand, in the asynchronous form, the use of the send operation is non-blocking, and the receive operation can handle both blocking and unblocking variants. In a scenario whereby maybe we look at the TCP, we can look at TCP communication or TCP protocol as a way of applying the synchronous form of communication, and UDP as a form of a way of applying asynchronous communication. But better still, let's look at these terminologies, right? So message passing may be blocking or unblocking, and this concept we need to really understand. What is this blocking and non-blocking? Yeah. So blocking is normally related to the synchronous communication. Yeah. So we have blocking send. The sender blocks the sending mechanism until the message is received. Here's a scenario whereby, for example, a particular process wants to, for instance, send a message to a process B. So when the message is in transit, the sending process A ensures that there is no any other operation that is going to be executed until, yeah. So that ensuring that there is nothing that is going to be executed is what we refer to as the blocking send. Yeah. So there's no send operation that is going to be executed until the message is received at the what? The recipient. Yeah. So that's what we refer to as blocking send. Blocking receive, on the other hand, when the receiver is receiving that message from the sender, it issues the blocking receive operation. So it allows the message to be received. Yeah, so it blocks. So it can't receive another operation, or before the message has already before it receives the entire message. So the concept of TCP, whereby the sending or the receiving computer, or actually process, ensures that the packet has been received in a sequential manner, checking its order of actually how it was sent. That allows it to block any other operation that's going to use or that's going to execute the receive. I think there's two concepts that are within the synchronous form of communication is well understood. Now, non-blocking, on the other hand, is considered as asynchronous. Yeah, and this is where we use the UDP form of communication. Yeah, so there's non-blocking that is executed during send, and there's also non-blocking that is executed during receive. Typical scenario is whereby the sending process doesn't really care whether the receiving process has received that particular message or not. With it, it will continue doing what? Sending to multiple processes. So it doesn't really have that leisure or time to block itself. Yeah, it allows the available ports, the available resources to keep on using the send mechanism, so that at least they don't really block their way of sending the messages. On the other hand, also the receive doesn't have the luxury or leisure of stopping other processes from sending or from receiving. Yeah, so it's an open system whereby the sending and the receiving processes are at liberty, yeah, to send multiple messages and to receive multiple messages without bringing barriers of blocking. That is the concept of what? Non-blocking. Of course, within the asynchronous, we can bring in on board the other aspect of blocking and unblocking, right? Asynchronous, we can also have a situation whereby, I think we are going to look at it, a situation whereby a particular sending process blocks the sending mechanism, but at the recipient, it allows it to receive multiple, yeah, messages in what we refer to as non-blocking. So we have also a scenario where we can have a process blocking the send mechanism, but again have the non-blocking receive mechanism in what we refer to as the blocking non-blocking mechanism, right? So we need to understand that for the sender, it's more natural not to be blocked after issuing send. Yeah, that is for synchronous. Yeah, so you need not really to can send several messages to multiple destinations, right? But sender usually expect acknowledgement of the receive. That's what I said. It's synchronization typically employs the mechanism that the TCP protocol uses, yeah, acknowledgement, yeah. And of course, for the receiver, it's more natural for it to be blocked after issuing the receive, yeah. So this is just trying to help us understand the concept of how synchronization communication happens. So the receiver usually needs the information before proceeding, but could be blocked indefinitely if the sender process fails before send. Right. Now we also have the other example that I was trying to illustrate. So there are other possibilities that are normally offered. Example, blocking send, blocking receive. This one can always happen. Yeah. So both are blocked until the message received occurs when the communication link is unbuffered, no message queue. So that's another scenario. Yeah. There's the other scenario that I was looking at, the non-blocking send and blocking receive. We can also have blocking send, yeah, and unblocking and non-blocking receive, right? So the third one, non-blocking send, blocking receive, yeah, giving an example here, the server process that provides services resources to other processes. Yeah, so it will need the expected information before proceeding, right? So with this understanding, let's look at an event diagram to help us understand how the two processes communicate synchronously and asynchronously. Yeah. So we have already mentioned the terminologies, how the blocking operation is issued, how the blocking is executed, and so on. So here, in this particular event diagram, you can see we have the client sender and the server receive. So here, they initiate the synchronous send and synchronous receive. Remember what we said, right, about the blocking and unblocking, right? So within the synchronous send, you can see that the red tip there of the arrow shows the operation. The execution flow is depicted by the blue arrow, and of course the suspension, yeah, is also illustrated using the dotted line, right? So when the process 1 execute the synchronous send, and remember we said that this offers the what? The blocking mechanism, right? So there's a blocking mechanism that starts, right? And also there's a blocking mechanism that ends, yeah? So when a process communicates within a synchronous or in a synchronous way, it offers a blocking option, yeah, within during the send, and also does the same blocking during the receive. We have already discussed this in our previous slide, so this is just a diagram that shows how this is implemented, yeah. So you can say the block happens during send, and the block also happens during what? Receive, right? And we have said that this blocking is just to allow the receiving to actually receive the message, and also the receiving process also blocks its operation to ensure that it receives that only message before it allows other operations to continue. We also have asynchronous send and synchronous receive. Take note of that. Asynchronous is associated with non-blocking. Synchronous is associated with blocking. So with that concept, we can now see process 1 providing asynchronous, right? And there's an unblocking send, yeah? So it keeps on sending because it doesn't block any operation, yeah? But on the other hand, the synchronous receive blocks, yeah? It offers some kind of way that it provides some buffer, yeah? It allows the receiving process to establish the number of packet that has been sent, how it has been sent. So it blocks and ensures that the operations at the receiving end is actually carried successfully. So those are the two operations, asynchronous and synchronous. And also we have now, this is the other way around, right? Synchronous send and asynchronous receive. Synchronous block, asynchronous non-block, right? So asynchronous send, here the process 1 now allows or actually blocks when this particular sending process is actually taking place, yeah. And also on the other hand, the receiving process has that particular liberty to keep on receiving different messages from different processes in what we refer to as non-blocking, right? So data from P1 was received by P2 before P2 issued non-blocking, right? So that's how synchronous send and asynchronous receive is implemented. We can also look at the other option where we have synchronous send and synchronous receive, right? So here data from P1 arrived to P2 after P2 or process 2 actually issued an unblocking receive. So it's I think it's also the latency that you're talking about, and maybe the communication aspect, yeah, that the two processes engage with during asynchronous and asynchronous send. The another scenario where we have the synchronous and asynchronous receive and send, here, as you can see from process 1, the data from process 1 is arrived to process 2 before process 2 issues an unblocking receive operation, yeah. At this juncture, process 2 is notified of the arrival. The notification aspect, yeah, now brings on board the kind of what? Acknowledgement aspect of the transport control protocol. It offers also the transparency that we have so far been looking at when it comes to how the distributed system actually communicates, yeah. We have another scenario where we have asynchronous send and asynchronous receive, yeah. So here uh, the blocking send is issued in process 1, but it doesn't need to acknowledgement. Yeah. So where there's a synchronous send and receive, there is no what? There is no acknowledgement. And this one now actually brings on board the concept that I was trying to tell you about the UDP, how UDP communicates what? Asynchronously, right? So this is what is being shown here. So in a nutshell, the event diagram that you have been looking at is summarized by two processes. Actually, process A are communicating with process B in a particular time frame, and a lot happens during communication between the two inter-processes, right? We could have some kind of delay or blocking mechanism, non-blocking mechanism, and so on. All right. Now, when the two processes communicate, normally there are challenges, as I mentioned, right? Maybe during establishing communication between two processes, we could have latency issues, maybe there could be network issues. Yeah? So the receiving process could not maybe get the message in a timely manner. Yeah? So we can prevent this through the use of timeouts. Yeah? So blocking operations is issued in the wrong sequence can cause also what? Deadlocks. Yeah? As there's a particular diagram here, it shows two processes continuously maybe are waiting and waiting. So the loop keeps on recurring. Yeah. So when two processes issues the blocking operation, yeah, without really maybe releasing that particular block operation, yeah, it could lead to what? A deadlock. And we can remove this deadlock by bringing on the timeout. So the timeout is established maybe after some period of time, let's say 5 seconds. If this deadlock is not really released after the 5 seconds, then the timeout comes on board, yeah, so that at least we can detect if there's a deadlock and eradicate those particular deadlock. So we can also improve this by ensuring that when using this, like if only blocking operation is provided for send and receive, then it is the programmer's responsibility to use child processes or threads. Now, in a normal scenario, the implementation of processes is normally parental-child kind of engagement. We have parent processes, yeah, the main processes, and you also have those processes that are associated with the main process, which we refer to as a what? Child processes. Now, it should be noted that when we have child processes, it's very, very hard maybe to terminate a parent processes. Yeah. So a programmer who comes up with maybe a particular API should program the interface taking note of this kind of association between the parent and the child what? Processes. So that when we have a program that will terminate the parent process, it should also take note of the child processes, so that we remove the deadlock in totality by eliminating the associated what? Child processes. I think that is well understood. So when you connect and receive two operations, it can result in indefinite blocking, as I would mention, and the only way the generally unacceptable is to really have some kind of indefinite removal of the deadlock. So we bring on board the concept of what? Time out. Yeah. So indefinite blocking may also be caused by a deadlock. So we have already looked at how we can have a deadlock being released through the use of timeouts. Yeah. So you can see, as you had looked at the first approach, where indefinite blocking due to a deadlock. Yeah. So P1 or process 1 keeps on waiting for process 2 data. Process 2 is also still waiting for process 1 data. So this should be eradicated. This indefinite blocking should be eradicated, right? Now, the interprocess communication requirements is simple. Yeah, We need to have a communication link, yeah, between the two processes. That's why we mentioned that infrastructure or communication media is very, very important, right? Also, we need to establish the messages that is going to be sent, yeah, and the kind of communication link, yeah, and the logical establishment of this kind of communication, right? So this is more or less the same as understanding how the various computer networks are implemented, right? Communication within local area network, communication within wide area network, and so on. So we can see we have taken a lot of time understanding one characteristic of inter-process communication, and that is synchronous and asynchronous. But since we have looked at all these added characteristics, such as message destination, when talking about synchronous and asynchronous, so we don't really need to take a lot of time. When a sending process releases a message, we need to append some kind of what? Like for example, the port number associated with the destination process. We could also append the addresses and so on, right? So message destination is another characteristic of inter-process communication. We also need to bring on board the concept of reliability. It is only a reliable communication link that is going to ensure that we have some kind of what? Communication between the two processes, yeah. And of course, reliability also bring in the concept of security, yeah. So integrity of data or message that is sent from the sending process, and also the receiving process should be upheld, so that whatever was sent is what is going to be received, right? And of course, looking at the point-to-point message service is we can be described as reliable only if the messages that are transmitted are guaranteed to be delivered despite some number of challenges that I've mentioned, like delay, latency, a packet being dropped on the way, and so on. And of course, the other characteristic of inter-process communication is the ordering process or operation, yeah. Looking at the TCP or Transport Control Protocol, offering acknowledgement and the desire of this protocol to ensure that the order at which or how this particular message was sent is actually received in the proper order. Talking about the checksum sequence, yeah. So if the message was having four, like let's say for example 4 segments, the receiving process should also receive it as 4 segments in the order that they were sent in, yeah. So those are the key characteristics of inter-process communication: ordering, message destination, and also asynchronous and synchronous way of communication. All right. So with that understanding, let's take note of also the other important aspect, and that is the sockets, right? Socket is one endpoint of a two-way communication link between two programs running on the network, yeah. Now, socket is normally bound between the two things, that is the IP address and the port number, yeah. Just like the normal socket that we normally have in our houses, yeah. When a particular process is establishing communication, it needs to identify, yeah, the IP address of the destination computer or node, and also the kind of port that is associated, yeah. If you are sending, for example, an email, yeah, you need to establish the end or the destination IP address of the computer, and again the right protocol or port that that particular email is going to use, yeah, when it's being received, yeah. So communication normally happens between two pair of what? Sockets, from the sending process to the receiving process, right? So the socket is very, very important, and that's why we need programmers to have some kind of what? Application interfaces that can help this communication implemented correctly. So The diagram here shows how a client is establishing the communication with the server using the different sockets. Take note of the IP address that is concatenated with the port number, right? So you can see the web server has its own port number 80. So ports are very, very important when we are communicating using the sockets. Yeah. So messages sent to some internet addresses and to some internet processes, internet addresses and port number can only be received by a process using a socket that is bound to this address and port number, right? So that is very, very important for us to understand. Now, also we need to understand that both forms of communication, like for example the two protocols, the UDP user datagram protocol and the transmission control protocol, use this layer of abstraction, yeah, to ensure that the sending or the two endpoints of communication really don't not taken through the technicalities involved when the two processes are communicating. You know? So inter-process communication consists of transmitting a message between a socket in one process and a socket within the other process. So there's a diagram here showing how the socket communication or how socket is implemented. As you can see, the entry point from a sending to a receiving process is through the what? The agreed socket, right? So it's very, very, yeah. We can also have the other available ports, yeah, ports that allows a process to maybe receive a particular email or send a particular email, download a particular file and so on, right? So those are the different sockets that you're talking about, right? Now, talking about communication between different processes, as I mentioned, synchronous communication, asynchronous communication uses the UDP, a way of what? Communication. Data, yeah, it offers connectionless way of communication. It doesn't offer guarantee whether the message is going to be delivered or not. It doesn't really care whether it has been received in the good or ordered way and so on, right? So for us maybe to ensure that we have some well established UDP communication, it's necessary to have a socket. Yeah, this one is going to help UDP communicate effectively between the client and the server, right? We also have the receive method, yeah, and also the message size. Yeah, when datagram communication is established, yeah, there's some kind of limitation that are related to this kind of use of datagram communication. Like it only allows up to 216 bytes of data, right? And if arriving message is too big for array or allocated to receive message content, truncation occurs. So those are some of the any application requiring messages larger than the maximum must fragment. So in any normal inter-process communication, there are pros and cons of using the UDP kind of communication. So we are not only saying that UDP has its downside, but also it has its importance. Yeah, we'll agree that communication between two processes that use UDP is very, very fast. Yeah, very, very fast. So when we have data, we have distributed system using UDP, you'll really have some very fast communication. Yeah, we also looked at the establishment of the synchronous and asynchronous, right, communication, right. So they suffer from failures as omission. Yeah, packets can be omitted, messages can be dropped, ordering is not taken care of, right. So the other hand, we have the TCP, and we say TCP comes on board to maybe eradicate the challenges that have been witnessed or realized within the UDP form of communication, right? So it would provide some kind of characteristics, yeah, like managing the flow control, yeah, establishing the message destination. It has the right message sizes. Yeah, it takes note of a message, the lost messages through acknowledgement and so on, right? So we looked at synchronous communication that offers the blocking. Yeah, it also has the process, yeah, matching of data items, right? So we can always associate the TCP communication with various protocols, yeah, that are connection oriented, right? Like you can use the simple mail transfer protocol, hypertext transfer protocol, right? And we can also associate these particular protocols with some given what? Port numbers, right? Like HTTP uses, I think, port 80, FTP, I think it's 23, and so on, right? Now, during communication between the two processes, we need to ensure that we understand how the external data is represented. Yeah. Now, the information stored in running programs is represented as data structures, whereas the information in messages consists of sequence of bytes. When you look at how TCP and maybe UDP communicate, yeah, during transmission, messages are normally organized or represented in some format. Yeah. So it's very, very important that the receiving process can actually decrypt or rather understand the messages that has been sent to it. Yeah. So irrespective of the form of communication used, the data structure must be to a sequence of bytes before transmission and rebuilt on arrival. So as the two processes communicate, they need to establish maybe the number of packets that's going to, or segments that are going to be delivered, how and on what manner. Yeah. So external data representation is an agreed standard that these particular two processes are going to use. Yeah. Maybe based on some kind of structure or values that they are going to append on this kind of what messages that is in transit. Yeah. So we can have, of course, we have other problems that can come on board, and I think that's what I mentioned. So we need to have an agreed external representation, yeah, that should support conversion, right? Like decryption or understanding, yeah, how this particular receiving process is going to maybe understand the content of this particular message. Yeah? So using senders or receivers formal format of communication in order to convert at the other end. So there are challenges that are represented during this kind of communication that need to be eliminated, right? And we can have this through marshalling of the various messages. Yeah. Now this is a concept whereby is the process of taking a collection of data items and assembling and disassembling them into a format suitable for transmission. Yeah, so one way of representing this external data is through use of marshalling, and of course, unmarshalling is form of disassembling, right? Assembling at the sending point and unmarshalling or disassembling at receiving point or the destination. Yeah. So the goal of marshalling actually is to ensure that whatever was sent is actually received in its original format, right? Yeah. And of course, how or the mechanism that the sending process used, like the converting of data structures, is the same way or same mechanism that the receiving process is going to use. Yeah. So in a nutshell, it linearizes the data structures for transporting messages and reconstructing the original data structures at the tail end of or during the destination. Yeah. So we can say that marshalling and unmarshalling activities are usually performed automatically by middleware layers. Yeah. So remember, middleware provides the abstraction or layer between the various application layers and the distributed operating system, right? So that at least there's some kind of transparency between the communicating processes. So we also have another way of presenting data, and this is courtesy of the common data representation offered by Corba. Yeah. So they represent data in different primitive values or using different like short bits. You can see there are different data types that are normally associated with the common data representation. Yeah. As you can see, this is how it is implemented. Yeah. So the sequence shows the length of that particular data or message, the value string, the array, and so on. So these are some of the two common ways of representing external data. That is use of common data representation and marshalling, right? So during communication, I mentioned also that the two processes can communicate remotely, right? If they are not within the same computer or environment. So we need to have some kind of remote procedural calls that facilitate the communication between two processes that are actually implemented in a network, right? Also, I mentioned about the stubs. Yeah, stubs kind of it kind of replicates, yeah, a particular scenario whereby instead of having a connection with the real or a server interacting with the real client, we can have a stub that offers this kind of mode of actual communication that a server is going to feel as if it is really connecting to the what? To the main client. Yeah. So we have also the other hand, also we have the stub clients and the stub servers. So programmers can always develop or create application that acts as stubs, and that's what we refer to as the what? The remote procedural calls. Yeah. So this particular remote procedural calls are localized. Yeah, they can be localized within the server environment or even within the client environment. Yeah, a situation whereby instead of a client interacting directly with the server, there will be a stub within the client local machine, so that the features that the real client or the real server present, they can always be implemented within a stub, right? So procedural calls offers a natural way to communicate, yeah, and that's why the idea where servers can export a set of procedures that can be called by client programs, yeah. So that's why we need some programmers or concept of programming where we can have these stubs implemented, yeah, properly, so that they offer interfaces that the client process can always communicate effectively with the server remotely. Yeah. So here the trick of implementing the RPC is to create stub functions that make it appear to the user that the call is really local. Remember the concept of localizing these operations. Yeah. So a stub function looks like the function that the user intends to call, but really contains code for sending and receiving messages over a network. Yeah. So it's a good way to actually implement this kind of remote communication between the two processes. So you can see there's client process implementing the client stub, and also the server process implementing the server stub. Yeah. So here is whereby the client can always have its operations well cut out in a local manner, and the same way the server can have the operations cut out in a local manner using this particular stub. So what are the benefits of having the stub? Because stub is actually the way that we can have these remote procedural calls, right? It offers some various procedure call interfaces, right? Writing applications is also simplified in that it hides all the network code into stub functions. The programmers also don't have to worry about the details such as the port numbers and so on, right? It also mimics or bring on board the kind of arrangement that the the OSI model present, yeah, open system interconnection, yeah, present. So this is a way. These are some of the benefits that you can always get when using the stub. Yeah. Now we can also realize some issues, yeah, within this particular stub. Yeah. But again, we need to ask these questions. How do we make this invisible to the programmer? Yeah. So what are the semantics of parameter passing that you can be able to use? Yeah. How are the different objects binded together? Yeah. And so on. How do we realize and deal with failures during the stub communications? Yeah. Right. So RPCs communicate through messages, yeah, and it's very, very important that we employ the use of asynchronous and synchronous way of communication between the two communicating processes. Yeah. So we have the various stubs. As I mentioned, you have the client-side stub that looks at the client as if it were a callable server procedure. We also have the server side side stub that looks to the server as a client side. Yeah. So the client program thinks it's calling the server. I think this is what I was trying to illustrate in my previous discussion, and so on. Yeah. So the stubs send messages to each other to make the RPC happen transparently. Yeah. So even if there's some major delay, these stubs tend to handle this nature of latency, eradicating other bottlenecks that will be realized during remote procedural calls. And that's the transparency, so that other objects will not really understand if there's a failure from the client side or there's a failure from the server side. Yeah. So there's a diagram here showing how this remote procedural call is implemented. Yeah. So as you can see, the remote procedural call only happens within the local stubs, right? And there's no really direct communication between the two client and the remote processes, right? So that's how the RPC works, and it can be executed by looking at how the client and the server share their messages, right, from this particular diagram. So user calls kernel to send RPC message to procedure X. So there's a back and forth way of executing the remote procedural calls that is implemented by through this particular diagram. So take note of the port numbers. Yeah, it should establish the message destination, as we had already talked about in our previous discussion. By using the stubs, now we can actually bring on board transparency, and that's what the remote procedural call is there to implement. Yeah, so it brings transparency so that the remote procedural calls look like the local procedural calls. Yeah, again, we have seen how it manages failures, right? Remote nodes networks can fail in more ways than with local procedural calls, so it needs extra support to handle failures as well, right? Because you can have the double tragedy. Yeah, when one stub fails or it's not really well implemented, performance could also be an issue. Yeah, so it also comes with its own challenges that we need to really look at. Now, the other method of how the remote or how communication happens remotely between different processes is through the remote method invocation. So they're more or less the same as the remote procedural call, yeah. But now here we can implement it over some kind of programs such as the Java, yeah. Like the RMI allows a Java program on one machine to invoke a method and a remote object. So through use of objects, the different processes can be able to communicate. Yeah, so we normally have the remote object references that are needed when a client invokes an object that is located on a remote server, as you can see. Yeah, and a remote object reference is passed in the invocation, a message to specify which object is to be invoked. Yeah, so this is some kind of arrangements between two objects using or referring to particular objects, right? So as you can see, how these particular remote object references have been implemented. Yeah, so there's a port number, internet address. Yeah, so the generic format of a remote object reference, you can see. Yeah, so it uses the internet addresses, the time, the object number, the interface. Yeah, so this is normally implemented when the remote object is actually invoking or requesting some kind of attention from other process, right? So talking about client communication, you've looked at the two common ways, the RMI and the RPC. Yeah. Again, we can also bring on board other concepts of how the client communicates via the UDP, yeah, or via the TCP. Yeah. So client and server can communicate through connectionless, yeah, way or method, or they can also use the connection oriented communication. All this is based on maybe avoid to offer acknowledgement to ensure that the information or the message arrived the way it was sent. Yeah. So remembering or what we looked at the beginning, we looked at the request reply protocol, yeah, that can actually be implemented to ensure that the client and the server communicate. Yeah, like for example, you have the do operation, get request and send reply. This one can be implemented when two processes communicate. Yeah, like for example, if you have the request reply protocol, yeah, it can offer the do operation, yeah, by sending the message. Then the server can always execute and so on. So there's a kind of back and forth using the request reply protocol. Yeah. So here is how it is implemented. As you can see, the do operation here sends a request message to the remote object and returns the reply, right? And of course, the get request acquires a client request by the server port. That's like when the server is actually trying to reply to the client, right? And of course, we have now the reply, yeah, where the server replies to the client through the given address, port, and IP address for that matter, right? So that's how it is the structure of the request reply protocol is the message structure. Yeah. So in a protocol message, normally the first field, as you can see here from the diagram, is the message type. Yeah. So it indicates whether the message is a request or a reply. The second field indicates the ID of a message, the message identifier. The third field indicates the remote object reference. And of course, the fourth field is an identifier for the method being invoked. Yeah. And that's why we need some kind of Java programs to be able to implement this kind of communication, right? So we have the message identifier, as you had already looked at. Any communication between the client and the server needs some kind of port number, yeah, or addresses, right, that the two communicating processes can be able to use. Yeah. Now there's a failure model that the request reply protocol normally use, yeah, so that it can try to eradicate the problems brought on board. Like we have the omission failure, yeah, that being presented by the UDP datagram, and also we have the messages are not guaranteed. So here's where the client server communicates via the UDP, right? Remember, it can also communicate via the TCP. So here also we have the RPC, uh, the protocols that the RPC uses. We have the request protocol. We also have the request reply protocol, yeah, and the request reply acknowledge protocol, yeah. So this is implemented based on the kind of communication that we looked at, yeah. Like when the client is requesting, there's a request protocol. When for example, the server is responding to the request, there's a request reply protocol, yeah. And of course there's also a request reply acknowledgement that happens, right? So RRA is based on the exchange of 3 messages, yeah, request reply acknowledgement. So this means that chances are there could be some kind of transmission control protocol being used, right? Lastly, not lastly, but to understand how this kind of client-server communication happens, we can use the HTTP as an example of request reply protocol. Yeah. So here is HTTP is a request reply protocol for the exchange of network resources between web and client. Yeah. And normally it follows the similar steps as we have seen. Yeah. Establishment of connection, right? Sending, right? And also the reply from the server, and then connection closure. Yeah, the same principle that any process normally execute when they are sending a message, right? So HTTP uses given methods. I believe we understand how this one is used. Like for example, we have the GET, request the resource identified by URL as argument. Yeah. So as you can see, a typical example there. And then we have the head. This method is similar to GET, but only metadata information is being returned, like the author information, the type of data, the size of data, right? We also have the post. Yeah. So this specifies the URL of a resource instance that can deal with the data supplied for the request. So it's more or less the same as using a form or a user populating a form, and then you click on the submit button. So that is a post operation, right? Then you put operation also within the HTTP, supplied data to be stored in the given URL, yeah, as its identifier. You also have the delete. Yeah, the server deletes any identified resource by the given URL. And of course, you have other options that are presented within that particular URL. Server also has the capability to trace back the request message through the trace procedure, right? So a reply message from the server typically provides the protocol version, status code, reason, some headers, and an optional message body, right? So if you happen to communicate between the client process and server process, a reply message will always offer that, right? So a basic HTTP protocol initiates based on the 2 processes. We have the web browser and the web server. Yeah, so we have looked at how the HTTP protocol provides this kind of communication between the sending process and the receiving process, which happens to be the server. So here's a typical HTTP session. You can see the date, the port number, the address, the GET method, and also we have the content, right? So here is a well represented HTTP session that you can always familiarize yourself with, right? So finally, we need to understand how various processes communicate with other processes in an operation known as multicast. Yeah. So As I had said, this is an operation that sends a single message to the different processes that belongs to the same group or processes. Yeah. Now, the good thing of offering the multicast communication is that it brings on board the concept of fault tolerant. Yeah. If we happen to replicate, or a particular process has options of communicating with different processes, so if there's a failure, it can always invoke other processes to carry out a given activity, right? So again, we looked at how the router can be able to establish if a link has a failure or not. Yeah. So by sending multicast messages to the various connected routers, it can establish which route is operational and which one is not operational. And the same concept applies to the servers and the clans. Yeah, the clans should always be in a position to establish which server is communicating and which one should they use in order to maybe to avoid latency issues, failure issues, and so on. So group communication offers better performance through replicated data, as you have seen, right? And also propagation of event notifications, just to ensure that they get the right communication, yeah, from the surrounding processes, right? So it uses the IP or the internet protocol to establish communication between the different processes. And of course, multicast is normally given some kind of reserve on a particular address, like the IP version 4 addressing scheme gives it a group, the class D, yeah, as the reserved way of implementing the multicast communication, right? So I think that will inform or bring us to the close of our discussion of how the various processes communicate, right? So you need to establish an